Hello. Today I'm going to be sharing a few different tips and tricks for simulation automation within STAR-CCM. The most important thing for a well-automated simulation is the use of simulation parameters, and these are just arbitrary constants that you can set in your simulation that you can import into practically any field using this function syntax within STAR-CCM. So here you can see I have parameters for things like rolls, ride height, corner radius, etc., corner direction. And the first place I'm going to use that is within the domain creation. Now I create my domain within the 3D CAD module within STAR-CCM, which is sort of a basic built-in 3D CAD software. So I'm going to my domain part. You can see that it is a revolve operation, and the first place I use those parameters is in the cross section for that revolve, where I just have the cross section defined using things like the height of the car, how many heights I want the domain to be above the car, corner radius, etc. And while not shown here, what you can also do is using an if statement, set one of these values to 0 if you have a symmetry value set to 0, or set to 1 rather. And that will just cut off half the domain and will give you a symmetry simulation. Now you might be saying, it's a cornering simulation, you can't really do symmetry. Well, if you set the radius to some absurdly high number, like say 500 meters, it's effectively going to be a straight line simulation with some of the relative flow angles maybe about 1/3 of a degree off, a acceptable sacrifice for ease of use. And in here, I also have different sketches and revolves that I use for different refinement volumes within my volume meshing operation. The next place I use the parameters is for the attitude adjustment of the car. So here I have different transform operations that I use to move all the geometry to get things like roll, ride height, side slip angle. And here specifically, I'm moving the domain around the car, which becomes a lot more convenient for things like post-processing to have everything focused on the car, as opposed to moving the car within the domain. Now, since I'm keeping the sprung mass of the car constant position, but I'm changing the wheels, that's going to present an issue when you have all those different rotating reference frames for the wheels moving around. So how I deal with that is I create another 3D CAD model for the wheel coordinate systems. I basically just make 4 blocks, move them into the position of the wheels, and then copy those same rotates, rolls, and ride height position adjustments that I have within my simulation operations, recreate that within 3D CAD, and then I can export coordinate systems just by creating a new feature, reference geometry, coordinate system by 3 points, and then just referencing those 3 points at each block. That creates an coordinate system that you can export to your simulation to use for rotating reference frames. Before I go on to post-processing, one thing that troubles a lot of people is oscillating results. Now, when you have separated flows behind things like tires or on your wings or in a heavy side slip, you're going to have some separated flows, and those are likely going to present issues with convergence and sort of getting a stable, dead set of forces and moments. Now, there's 2 ways we can deal with that, depending on what you're trying to average. With your report monitors, what you do is you can create a statistics report, just new report, user statistics report, and you can just reference that to a monitor that you have you're trying to average out. So going to my forces, or sorry, rather my full car forces, I have the CDA mean statistics report that I have referenced my CDA monitor. And in order to start the averaging for that, you have to use, or I use what's called a simulation event. And what those are is or update events rather. And what those are just arbitrary things that trigger in the simulation that you can use to trigger other different things. So I have two here, one that triggers a single time after I pass a certain threshold iteration, and one that triggers each time there's an iteration past that certain threshold. So this is the one that triggers once, it's the specific monitor value, and this is the one that triggers each iteration after. Now the one that you use for reports is the single trigger, and the one that you use for field mean monitors is the one that triggers each time. And I guess I got a bit ahead of myself. For averaging out field functions, you'll use a new monitor field mean, and from there you just reference the field that you're interested in averaging. And for vectors, you're going to have one for each of the I, j, and k component, and then you'll use a custom field function to recombine those. What I'm doing here is I'm actually taking the variance of some fields and also publishing the mean, and I use this to kind of see which parts of my simulation am I getting those oscillations in, which areas are presenting the most trouble for convergence, in terms of getting a steady state answer as opposed to an oscillating one. Heading on to post-processing, I'm sure many of you are familiar with just looking at the pressure coefficient along the surface. Now I'll stress to use a pressure coefficient. Using absolute values of pressure can be really hard to compare across different speeds and see what your Reynolds dependency is. And this is sort of a universal language, if you will, for aerodynamics. So I'll stress very much so that it's important to use pressure coefficients. It just makes life easier. Now this scene will look kind of familiar for you, many of you, and one handy thing is to use set views. So you can just set an arbitrary view that you want to save for later, store it, and you can restore that view whenever you want, and that way you can have things be very consistent. So I'll have some of the basic ones like the side view, top view, etc., etc. Going back to the one I had before. And one thing that I find really handy is to export, show the parameters I have on the screen. So when I'm exporting this image, I can know which sets of parameters this is corresponding to. Now note that if you change the speed or the roll or the write height parameter after the fact, it will update in here. So for example, I ran the simulation at 15 meters per second, but I updated the speed parameters, now it actually shows 30. So you have to be careful with that. And how I do those is I just create a report, and it's just an expression report, and from there I reference that parameter that I have created in the simulation parameters. And the syntax with that is just to use a $, then curly brackets around the parameter name. And it'll be green so you know it's working. So that's what I use for all my different scenes. And another really good scene to have is the line integral convolution. This is the wrong one. And you can use that to view the direction of flow across the surface of the car and be able to spot areas of detached or separated flows and give you an idea of where the flow is moving around the car, which directions. Really handy for design work. Now you just create that by creating a vector scene of the car and looking at the wall shear stress, but that will by default give you a glyph representation. Now I don't know about you, but that isn't too handy for viewing at. So I always switch to a line integral convolution and then change the number of steps from the default of 15, which is a bit coarse, to 30, which I find to be a lot finer. And here I have a custom color map with a pink band at really low values of skin friction that I use to highlight areas of separated or weak flows. A third visualization is use of total pressure sweeps along the X direction of the car. And these are really crucial for seeing what's going on with the off-body flows and tracking losses as they move along the car. So with this, you're going to want to enable the animation for the plane that you're using to view the scene. And you can either export this as a video, so movie file, or you can export them as PNG frames to use for later. Third way is you can also just view it directly in the simulation, although depending on your simulation size, that can be quite choppy because you're viewing, millions of cells live. But here you can see some stalling going on in this footplate vortex that you wouldn't otherwise see in the skin friction. Actually, going back to skin friction, one thing worth noting is that here I display the vectors for the wall shear stress, but then I actually color it by the skin friction coefficient because I really like those normalized values. And to do that, I just change the color mode from the vector magnitude, which is the default, to a scalar field. Now, going on to simulation sweep automation, for that I use very much so the Design Manager project feature, which you just kind of right-click the simulation at the top of the tree and then create Design Manager project. And here I already have that. I've already ran a sweep, so I can give you an idea of that. So here you can basically just sweep those parameters that you set up in your simulation, and STAR-CCM will just run all the different ones that you want them to, and it will present you with whatever results that you're interested in seeing. For example, I have swept the slide slip angle from -10 to 0 degrees, and then I can set all those other values as constants. So I'll have 10 simulations to run, some of which failed due to some meshing errors, unfortunately. And then I have all those different outputs that I've told the sweep to keep. You can also save certain scenes and plots from your simulation. For example, if I want to look at, what's the convergence like for a given study, I have saved residuals that I could view for later and make sure nothing is going funky there, as well as viewing the forces to make sure that they actually have converged and their mean values have converged to a suitable level. And the same thing with scenes. You can either export hard copies or actual 3D representations to view for later. So here I've actually saved the 3D view, although it can be quite expensive when you're doing larger sweeps. You can also plot your different sweeps. For example, I can look at the side force versus the side slip and look at the relations there. And all this data that you generate within your sweep can be exported to lab time simulation software to get all of your error maps. So it's just a matter of anytime you have a new geometry that you want to look at the error map of, it's just a matter of updating a geometry in the simulation, sending it back off to the cluster and having it run, and then coming back to automatically created results that you can use.